in this scene, these characters are discussing the interference of from solar flares because of heightened sunspot activities on communications networks. Indeed, if you go back to 1960s and look into the scientific literature at that time, there used to be an IEEE journal, IEEE Transactions on RF Interference, and a number of papers that were published around that time in that journal were about this problem. That is the interference from solar flares on communications networks. Here is a sample paper from that journal on this topic. This is an example of natural interference. Today, we are going to discuss about man-made interference from one emitter to another emitter, that is from radar to communications or positional navigation systems or vice versa. Indeed, these kind of studies on RF interference across the spectrum, we can date them back to 1960s or even before that. The very first paper on joint radar communication system, very rudimentary method, indeed appeared in 1963. In late 1970s, NASA investigated this problem that, okay, if we are going to operate different types of sensors in the same part of the spectrum, then there is going to be interference from one to the other. So can we combine them as a single system so that there's no interference, or we can manage interference? So they studied this for the shuttle program in very late 1970s and early 1980s. But the primary research in this topic really started in mid-1980s. Around that time, US Army was deploying this one particular radar system, which we call as FOPEN radar system, or foliage penetration radar across US. And that radar operates in UHF-VHF band, and it is used to detect intruders hiding in very deep forestation areas, deep vegetation areas. At that time, they started encountering interference from TV and broadcast stations while deploying this radar. Since the transmit bandwidth of this radar is very wide, engineers came up with a simple solution that let's put notch filters at the receiver at the interfering frequencies and then get rid of this interference. And that didn't cause a lot of signal degradation or distortion because of this very wide transmit bandwidth. Then in early 2000, we see some more research coming up on spectrum sharing or coexistence and so on. But it's really in past 15 years that the activity in this particular domain has exploded exponentially. And we are going to first examine what are the reasons why people are suddenly interested in this now, even though there has been decades of interest in this area, at least scattered interest, but why suddenly this topic has become very important now. So there are several motivating factors, but we'll discuss two major drivers to this research, one from the communications perspective and another one from radar perspective. So from communications perspective, the interest in this in ISAC comes from the recent trends in wireless communications. As you can see from the graphic on this slide that I've taken from some industry sources, the number of devices that are right now connected and exchanging data with each other, that has already crossed hundreds of billions. And this number is supposed to rise exponentially in the near future. So more devices connected means more data exchange. So we need protocols that can sustain that high data rates. Apart from this, high data rate also comes from the expectations from next generation wireless communications networks that they support very high-end applications related to infotainment, gaming, and so on, and provide a very high quality of service. The kind of data rate that is expected because of these factors is so high that the current sub-6 gigahertz or traditional wireless communication systems, they are unable to sustain those kind of data rates. So how can we meet that demand? For that, we only turn to Shannon's famous capacity formula as a guide, which tells us that the capacity C, which dictates the data rate, is governed by three factors. First is the lowercase n, which is the number of orthogonal or non-interfering resources. Could be the number of time slots, subcarriers, number of antennas, and so on. Second is the signal to interference plus noise ratio, or SINR, but you will have to increase SINR a lot to see any appreciable increase in capacity because they have a logarithmic relationship. So we come to the third factor, W, or the bandwidth. Wider the bandwidth, it is better for the capacity or data rates. But then bandwidth is a scarce natural resource. We have limited amount of spectrum that we could allocate to just one particular application. So we have to find a way to efficiently utilize the bandwidth because everyone wants wider bandwidth. As you can see from this graphic at the bottom that I've taken from Ericsson's white paper published a few years ago, right now the current 5G spectrum range is in the centimeter band, or the so-called sub-6 gigahertz band, which is very crowded, as we had seen in one of the slides that Mehmet had shown earlier. So how can we have more spectrum or wider bandwidth for some of these applications? One of the solutions that has been suggested is that you move up in the frequency bands, that is to millimeter wave or the so-called sub-terahertz region of the spectrum, where depending on which country you are in, you can have anywhere from 4 to 15 gigahertz of contiguous bandwidth. So at sub-6 gigahertz, the carrier frequency itself is 6 gigahertz. And here we are talking about bandwidth from 4 to 15 gigahertz. Of course, we have to develop technology to harness that bandwidth because attenuation is very high in those bands. But this contest for wider bandwidth, that is not new in communications industry, as you can see from some of the headlines that I've taken from newspaper site from 1980s to very recently. Wireless service providers have been asking for more spectrum from the government for quite some time. And now there are more players. So this problem is more industry players. So this problem is becoming only worse because everyone wants wider bandwidth to support high-end applications or to provide connections between different devices. But we don't have enough bandwidth to allocate to only one industry service provider. The second motivation for ISAC is from the radar industry or radar researchers. Now, radar engineers have been using all parts of the spectrum for a very long time. So the primary motivator here is really the automotive radar industry. As you can see from the graphic here, modern autonomous vehicles, they are highly sensor driven. They are equipped with many sensors like GPS, LiDAR, cameras, radar, ultrasonic sensors, and so on. And the goal of these sensors is not only to guide the driver in a challenging or crowded traffic environment, but also to monitor the general health of the car. We have sensors for tire pressure, air conditioners, and so on. As I said, highly sensor-driven system. Sometimes also to monitor the physiological behavior of the driver or other occupants of the vehicle. So we have in-cabin sensors that can measure the heart rate, respiration rate, or other kinds of vital signs of the occupants of the vehicle. But if we confine ourselves only to the autonomy aspect of the vehicle, then chiefly three sensors are common. First is a high-resolution camera, provides a very good visual, has a lot of semantic information in its files. But then its performance in low visibility conditions, whether at night or in the presence of precipitation, rain, snow, then it deteriorates. And it does not measure Doppler velocity directly. It only infers it indirectly by looking at the changes in the motion or the position of the vehicle across different frames. So it's an indirect measurement. However, when you're on the road and you're in an autonomous vehicle, we want very accurate measurements because it's a life or death situation. You might have seen this type of headline where I've blurred the name of the vendor, but you can guess if you Google it, which appeared just a few months ago. And this particular vehicle is equipped only with cameras. I'm not implying that that was the reason for the crash, but it is usually one of the factors in such kind of situations. So we come to remote sensing sensors, that is radar and LiDAR. Now, LiDAR operates in the optical range, very wide bandwidth. People who work with signal processing related to remote sensing may recall that wider the transmit signal bandwidth, higher is the resolution of the sensor. By resolution here, we mean the ability of the sensor to discriminate between two very closely spaced targets. So LiDAR has a very high resolution. However, the problem with LiDAR is, A, it is an expensive sensor. A few years ago, General Motors presented a white paper which stipulated that the cost of remote sensing sensors for autonomous vehicles in batch production should not exceed $100, and LiDAR does not meet that benchmark currently. Although there is a lot of research going on in manufacturing cheaper LiDARs, but we are not there yet in the commercial domain. It also is a mechanically scanning device, not electronically scanning. Again, it's in a research domain right now, electronically scanning LiDARs. We haven't seen a lot of commercial implementations. And it is also mounted outside the main body of the vehicle. So some vendors, they don't like it for aesthetic reasons. So we come to the third sensor, which is radar. It's a low-cost sensor, meets that General Motors benchmark, operates on Doppler principle, so measures Doppler velocity directly, unlike a camera. Low-cost, all-weather sensor. The problem with radar is it operates in the microwave range, where the bandwidth is limited. Hence, its resolution is poorer compared to LiDAR. The only way we can increase that is if we allocate more bandwidth to radar. That was one of the reasons why automotive radar manufacturers, they went from the initial implementations in K-band to the current implementations in the millimeter wave band. But we want to provide even more bandwidth. There's a lot of research going on in low terahertz automotive radar and so on. Second aspect of autonomous vehicles is we have this concept of connected and automated vehicles, software managed functions. They are supposed to talk with each other, like vehicle-to-vehicle communication or to satellite or to traffic infrastructure. And because of all of these additional functionalities, they generate a lot of data. As we have seen before in the communication segment of the motivation, more data means you need protocols that can sustain those data rates, which the current short-range wireless technologies, which operate again in the sub-6 gigahertz region, like DSRC or CV2X, they are unable to sustain these kind of data rates. So we have this problem. If we want to sense accurately with these autonomous vehicle radars, then you need wider bandwidth, because then higher the resolution. And if you want to enable the functionality of connected and connected vehicles in autonomous systems, then also you need higher bandwidth to sustain these kind of data rates. But we don't have enough bandwidth for just to allocate this one to this one application. So the way forward is that radar and communications, they should somehow learn to share the bandwidth. This can be achieved in a variety of ways. They could coordinate their transmissions, but then that means it would not be a seamless transmission for either one of them. It's only when one function does not need access to spectrum, only then the other can access it. But if the other, both systems, they need that part of the spectrum, then there's a conflict, then there's a problem there. Another way is use the same type of hardware at the transmitter and receiver, same waveform. But then those kind of systems are quite complex to handle, although we'll see an example in this talk later on, how to handle those kind of systems, common hardware, common waveform, and so on. But how pervasive this problem is right now. So if we look at the current spectrum allocation, as you can see from this table, currently pretty much every IEEE radar band has some coexisting communication service. And this problem is only becoming worse because we have new communications technologies that come up every few years in different parts of the spectrum. And we have new types of radar applications too. So automotive radar, they were not very common 20 years ago, but today they have become very common on the road. We have weather radar deployments increasing in X band, KUK band, where earlier those deployments were not there, and so on. But this problem is not just an engineering or a research problem. It also has implications in policy, regulations, and even in the legal community. So there have been two very famous court cases recently. In 2021, FCC allocated slivers of sub-6 gigahertz band to unlicensed users. And because of that, AT&T sued them because their 5G spectrum range was nearer to one of those unlicensed users' band. Second court case was in 2022 when FAA asked Verizon to stop transmitting their 5G frequencies near airports because that transmission was interfering with this device that aircraft have been using for decades, which is called a C-band altimeter. So this example actually demonstrates that the problem is not just radar or communications, but it extends to other devices as well, like altimeters. There have been complaints from radio astronomers that the interference from satellites is hindering the clean sky observations for them. Even meteorologists are looking into this, as you can see from this article from Lincoln Lab, the threat from Wi-Fi to weather radars, where sometimes that interference from Wi-Fi has been misconstrued as a storm, falsely detected as a storm. So this problem is now across many different applications and has implications beyond just the research or engineering domain. So recognizing all of this, DARPA about 12 years ago launched this program called SSPARC to develop spectrum sharing technologies between S-band military comms and S-band military radars. And after the success of that program, National Science Foundation has extended these investigations across all the bands, and some of their programs that, and they're still going on. I've listed them here: SWIFT, NERDS, PART, Spectrum X, and so on. And in fact, every year I see a call from NSF on some problem related to coexistence, spectrum management, or ISAC. So clearly the problem is very important, and this we are just looking at the US landscape. If you go to Europe or even in Asia, there are different programs right now that are being undertaken by various government agencies to address this problem. All right, so after the launch of SPARC in past 12 years, a lot of solutions have been developed, and now we are going to examine some of them. Very broadly, if I have to classify these spectrum sharing solutions, so as I alluded earlier also, one way to classify them is whether the hardware is shared at transmitter and receiver or not. So this diagram is from our very popular paper that appeared in Signal Processing magazine. So this broad classification, if we look at it, then if neither the transmitter nor receiver of radar and communications is shared, then the solution that we get is that figure A. So radar and communications, they transmit from their systems independent of each other. Obviously, at the receiver, there is going to be interference. In this kind of topology, which we call as spectral coexistence, most of the research is focused on developing novel receiver signal processing algorithms to mitigate the mutual interference. We don't work on the transmitter much in this case. So this approach is very good for legacy systems, which have already been deployed very widely, and it will cost a lot to change the hardware completely. So what is preferred is that let's work on the digital domain on the signal processing side to mitigate the interference. That by no means imply that this is an easier solution. We'll actually see a very hard version of this problem in a bit. But this has been in use for at least 20 years. I mean, you can find literature on spectral coexistence from early 2000. Everything else where some part of the hardware is shared is called spectral co-design. A very general version would be figure D, where I've taken an example from an automotive scenario. We'll examine this particular example in more detail in a bit. So here, I have a red car, which is the common transmitter for both radar and communications. So it is transmitting a radar waveform that is embedded with the communication symbols. Then that waveform interacts with other cars in the surroundings, like the blue car or the yellow car, which we'll call them radar targets for this particular segment. And when that waveform is reflected, it is intercepted by a common receiver, which is the gray car, different than the transmitting car, which is the red car. So that's why we call this a bistatic system, because the transmitter and receiver, they are not on the same platform. Now, the goal of signal processing at the gray car is to extract parameters related to the radar targets. That is the location, Doppler velocity, or any other useful information it can get about the blue and the yellow car. as well as B, to decode the message, communications message that was sent by the red card, because it's a common receiver for both radar and communications. So this is a very general joint radar communication system. So it's bistatic, but you can also make it multistatic, multiple receivers, multiple transmitters. That would be an even harder version of this problem. So now, if I looked into only those four broad categories, and we have about 12 years of post-SSPARC research. So you would say, okay, these are four paradigms, people would have solved this problem by now, but that is not the case. That is just one type of classification that is based on the sharing of the hardware, but you can have many different versions of ISAC based on the waveform could be separate, then you get another classification, even though the hardware is the same. You can have the same hardware or different hardware, but a common waveform. Or it could be the same waveform, but shared on a time slot basis. So each time, in each iteration, we have a different type of ISAC system that we would have to design and then solve the signal processing problems for that. Now, based on the locations of transmitter and receiver, could be co-located on the same platform. Bistatic, we just saw in the previous slide, could be extended to multiple transmitters, multiple receivers. They may or may not be networked. Even those nodes may not be identical. One radar could be a mechanically scanning radar, another one could be MIMO, then a phased array. So it could be a heterogeneous kind of ISAC system as well. Usually in joint radar communication system, we are interested in optimizing the performance of both radar and communications, but there could be some cases where you may be interested in primarily just the performance of radar. So you optimize the performance of radar while accepting some deterioration in the performance of communications. Those solutions are called radar-centric. Vice versa, you get communication-centric solutions. We'll see a very interesting case toward the end of this talk, which is opportunistic ISAC, and which Mehmet also mentioned, signals of opportunity, where we have an existing system. Let's say we have a radar system, and we want it to double that system up as a communication system as well, without much change in the hardware. So that would be called opportunistic ISAC. And then depending on various different types of radar and communication systems, you can get other solutions as well. For example, if both radar and communications, they are MIMO, then we get joint MIMO radar, MIMO communications. There's a lot of work on this. Now, there is recent interest in in-band full duplex ISAC. So we have also done a lot of work on that. I won't cover it today, but I'll provide some references on IVFD ISAC. Some speakers mentioned about metamaterials, metasurfaces, reflector arrays. So we have done a lot of work on intelligent reflecting surface-aided ISAC. In fact, that is a topic of its own. Again, I'll provide references on this. Usually I do a talk just on the IRS-aided ISAC. And then which part of the spectrum you're working on, you get a different solution. So millimeter wave, we'll see an example later today. Low terahertz, there is also work in the visible light community on not exactly radar communications, but joint visible light positioning and visible light communications. And then there are some papers from quantum community as well. In fact, there are about 15 different IEEE societies which have published literature on ISAC or have some task group related to that. Even non-IEEE societies, such as American Meteorological Society or IRSI, International Union of Radio Science, have some focus groups or they have published some literature related to this. So clearly this problem goes beyond many different communities and is a very important problem, can lead to many masters and PhD theses as well. Now the question is why we have so many different types of solutions. That the reason is because we have a lot of different types of radar applications, and we also have many different communications protocol. And whenever you want to share spectrum between any two of them, then it usually leads to a new or a bespoke ISAC solution. That's why there's so much research that is getting published on this topic every day, actually. Okay, so with that as a background, now I'll take one example each. So we'll start with spectral coexistence, where I'm going to talk about this very interesting example of dual blind convolution. And then in spectral co-design, I will go into some more details about that automotive ISAC example, the biostatic case that we had seen earlier. If time permits, we'll look into terahertz ISAC. So I don't have that panic button, but I'll just, if I don't get time for terahertz ISAC, we'll go to that last example on opportunistic ISAC, and then I'll close it with some more references and talking about what are some other trends in this research. So, and as we move from coexistence to opportunistic ISAC, we'd also move from a very theoretical signal processing example to a very practical example, so that it gives you an idea of not just different types of ISAC topologies, but also right from theory to practice. So let's look into dual blind deconvolution. This is a problem we have been working at Army Research Lab for past few years. Before we understand what is dual blind deconvolution, let's just very quickly look into how traditional communications and radar operate in terms of this convolution operation. In traditional radar, we transmit the waveform. So we know what waveform it is. We have full knowledge about the waveform. We don't know the target profile, which here we'll call it as a radar channel. The waveform then interacts with that radar channel, and at the receiver, we get a convolution of the transmit waveform with the radar channel. With the knowledge of the transmit waveform and these received measurements, we try to estimate the unknown radar channel. This is the classical deconvolution problem, which was described by Norbert Wiener himself in 1948. Imagine a case where you don't know the transmit waveform as well. That could be the case with passive radar, could be the case when a hostile entity is transmitting that waveform. So we have no knowledge about the waveform. Then at the receiver, you have the convolution of unknown transmit waveform with the unknown radar channel. Both are unknown. And just by looking at the measurements, we would like to estimate both of them. This problem is called blind deconvolution problem. It has a very rich research heritage in signal processing right from 1970s. But in past 10 to 12 years, we have seen a lot of work on that topic, where people have tried to use the sparsity of the channel to decode both the channel, to estimate both the channel as well as the transmit waveform. So that is blind deconvolution in radar. In communication, something similar happens. Traditional communications, we estimate the channel a priori. And at the receiver, again, you have a convolution of the estimated or the known channel with the unknown transmit message. It is the transmit message that is unknown in communications. So that is standard deconvolution. But in vehicular communications, the channel is very dynamic because of the mobility issues. So in that case, even if you estimate the channel a priori, it becomes outdated very quickly. And you will have a situation at the receiver when you don't know the transmit message and you also don't know the channel. Then that is the case of blind deconvolution. Now, this is separate for both radar and communications blind deconvolution. What if we are operating in the spectral coexistence domain, where both radar and communications are blindly deconvolved? Then you get the problem of dual blind deconvolution, which is what I've encapsulated in this very first equation here. So we have the received signal in continuous time domain, YT, which is the superposition of those two convolutions that you see there. The asterisk here denotes the convolution operation. And the subscripts R and C are for radar and communications. X is the transmit signal. H is are the respective channels. So we don't know all those four variables. All we know is YT. With the knowledge of YT, how can we estimate all four of them? So in general, this is impossible because there will be so many combinations of those four variables, XR, HR, XC, and C, that will map to the same Y. So this is called an ill-posed problem. You cannot solve this because there are infinitely many solutions. The only way we can solve this is if we have some knowledge of the structure of X and H for both radar and comms. That's the only way forward to solve this. Of course, you can extend this to n-tuple blind deconvolutions if there are multiple radars, multiple communications. But let's first look at dual blind, and then I'll provide a reference how we can solve the n-tuple blind deconvolution. So let's just focus on this dual blind case. So as I mentioned earlier, we should have some knowledge of the structure of these signals. Then this problem is somewhat solvable. So that's where we started. Let's start with the structure for the radar channel. That is the gray box. So we assume there are L targets in the scenario, and each target is characterized by its complex reflectivity alpha R, which is related to the size, shape, or the material of the object or other material properties. Delay time tau R, which is directly proportional to the range of that target with respect to the receiver. Doppler frequency nu R, which is in the exponential, which is directly proportional to the Doppler or the radial velocity of the target. This is a very standard delay Doppler target profile model for a radar. For communications, a very similar model applies. So assume Q paths, so Q not equal to L necessarily. Assume Q paths, and then all paths they are characterized by a complex reflectivity, delay, and Doppler. That is also a standard communications delay Doppler channel model. For the transmit signals, in case of radar, we assume it's a pulse Doppler radar, very commonly used radar system, which is transmitting a train of P unknown pulses. Each pulse is ST. Now, you may say it's blind deconvolution. How do we know there are P pulses? Well, you can count the number of signals you are admitting at the receivers, at your receiver. So you would know P that way. You may not know the pulse repetition interval T, capital T in that one, but then you can again estimate that using period estimation algorithms. So here I'm assuming those are known, because even if they are unknown, there are easier ways to estimate them. So once we know those things, let's focus on a harder version of the problem. For the transmit communication signal, we assume it's an OFDM signal. So you can see the form there. So what we are going to do is we are going to estimate the communications message GP. That's what is unknown. We're not going to decode it. If you are additionally interested in decoding it as well, like in the constellation, then there are blind decoding algorithms, which have been researched in 1990s, blind decoding, blind equalization. So once we get GP, you can apply those algorithms to further decode it. We'll stop at just estimating GP. Now, with this structure, once I have this structure, I put it in the first equation. I discretize it, I sample it, and then after a few pages of tedious algebra, whose details you can find in our paper that appeared in the IEEE Journal of Selected Areas in Information Theory last year, we get this last equation, which is a simplified version, except that now it has a structure. Earlier we had no structure, but now here we have a structure. So here discrete samples Y, they have all these unknowns. All the channel parameters are unknowns in this last equation, and obviously the transmit signals are unknown. Now we have this model, but we still don't have an algorithm to estimate this. So how do we approach a way to actually estimate all these unknowns? Before I tell you what algorithm we use, let's make observation of some other things related to this structure. First, the channels are sparse. So there are only L targets, there are only Q paths compared to the number of pulses and number of range measurements that we are admitting at the receiver. So channels are sparse, so that means we can make use of sparse reconstruction algorithms. Second is that is on the channels. About the transmit signals, we mildly constrain them to lie in a known low dimensional subspace. What this particular assumption is what is also known as the lifting trick in signal processing. We see this in phase retrieval problems, super resolution, blind deconvolution, all those ill-posed problems. There are applications of this lifting trick. What this does is that we have, if you recall the last equation in the previous slide, it was a system of linear equations, but with a lot more unknowns than the number of samples you may have. What this does is it translates that kind of problem into a problem where we would be recovering rank 1 matrices. Like you just recover one matrix and that matrix encapsulates all the unknowns instead of trying to recover each unknown individually. And that is somewhat a tractable version of this problem. So once we have this additional aspect taken into account, then again, after a few more pages of algebra, you get this very compact sensing model, where the discrete samples Y, they are superposition of two linear operators, aleph R and aleph C for radar and communications respectively, which are functions of random matrices ZR and ZC. And those ZR and ZC, they have all the unknown variables of radar and communications. If we recover ZR and ZC, we can get those unknown variables. That's the idea here. I would like to draw your attention to the structure of ZR and ZC. As you can see, they contain the complex exponentials, that is e to the power j2 pi. From Euler's formula, we know that we can write this in terms of sines and cosines. In other words, we are dealing with trigonometric polynomials. So that word sounds like very mathematically obscure kind of polynomial, but we deal with them in signal processing all the time. DFT is an example of that because you have complex exponentials there. But here we are going to make use of some very interesting properties of these trigonometric polynomials. How we are going to use that, and we'll see that in a bit. But what is the next step? Once we have this signal model, how do we recover our signal? What is the algorithm to use? So we are going to make use of, because we have sparse channels, so we'll make use of sparse reconstruction algorithms. Normally, when only channel is sparse and it is only one system, not radar and communications together, just either radar or communications, we can apply L1 norm minimization. That has been a classical sparse reconstruction algorithm for a very long time. But here we have two systems combined together, radar and communication superimposed. And the sparsity is not just in one domain. It is not just in delay domain or the range domain or in the Doppler domain. It is jointly in both domains. So it's a little bit more complicated. It's higher dimensional sparsity. So we are going to use a generalization of L1 norm, that is the atomic norm minimization. It was suggested about 12 years ago. And it is very good when we are dealing with these general forms of sparsity. Apart from that, we are also dealing with the estimation of continuous value channel parameters. So if there is a fighter aircraft, it may be flying with a velocity of 308 meters per second. But normally when we want to estimate that in standard radar systems, we take the FFT of the spectrum, right? We take the FFT of the samples, and then we try to locate where the peak will be, and then we translate the location of that peak to the Doppler velocity. That requires binning the spectrum. DFT requires binning. So if the bin size is 10 meters per second, your aircraft may be flying with 305.6 meters per second, but you can only estimate it as either 300 meters per second or 310 meters per second because of binning. But here we know that in reality, these parameters are continuous valued. So we cannot use those kind of techniques, DFT, to estimate spectrum here. We'll use atomic norm minimization, whose applications in spectral estimation previously have shown that it is very powerful in estimating continuous value parameters rather than these discrete values. So that's another reason to use atomic norm minimization. Okay, so we write our atomic norm minimization optimization problem. Since it is not a standard atomic norm, rather it is a combination of two, one for radar, one for communications, we are going to solve for the minimization of sum of atomic norms. So those are two atomic norms that you see in this box here, the primal optimization problem, one for radar, one for communications. So that is one departure from the standard atomic norm minimization. Second departure is those atomic norms, they are higher dimensional because of the sparsity in both delay and Doppler domain. So that is the second departure. So we write this primal optimization problem here. Let's minimize the sum of these two atomic norms subject to our observations Y, which are known to us. If it was a standard atomic norm in one dimension, then we know how to solve this problem. You can write the semi-definite program for this to solve this problem directly. By semi-definite program, you will, some of you who have worked in optimization theory may recall that if we have SDP, then you can go on a computer and write a code for SDP. Something as abstract as this, you can't write a code. So our quest here is to find a semi-definite program for this problem. So we can't do it directly for this because of these two things. It's a sum and it's in higher dimension. So how do we solve this? People who work in optimization theory may recall that if the constraints are equality constraints. So here we have equality constraints, y equal to something, the observations. Then there's something called Slater's condition that holds, and we have a strong duality. That means if you're unable to solve the primal, because it may not be directly tractable, you can look at the dual problem. You take the Lagrange of the objective function and you look at the dual problem. Since there is strong duality, if you find a solution to the dual problem, it gives you the exact solution to the primal problem. That is what our strategy is going to be here. We'll look at the dual problem now. And that's where this trigonometric, the very beautiful theory of trigonometric polynomial comes in. So a very quick departure from this, a very brief interlude on which property we are going to use from the theory of trigonometric polynomials. So in 2007, Professor Bogdan Dumitrescu from Tampere University, he published this excellent book, which is titled Positive Trigonometric Polynomials and Their Signal Processing Applications. So there is this property there. Suppose I have a trigonometric polynomial, that is, I have these complex exponentials. So z would be that complex exponential. And the coefficients are rk. So if I know Rk, I know the full polynomial. If I know the coefficients, I know the polynomial because we already know what Z is. That is the complex exponentials. If it is non-negative on the unit circle, or in other words, it's a positive trigonometric polynomial, then the property that we have is that those coefficients Rk, they are completely characterized using a positive semi-definite matrix Q. So I can write Rk as the trace of the product of elementary Toeplitz matrix theta k and Gram matrix Q. In other words, if there is something that I have to find out related to trigonometric polynomial, I have to focus only on its coefficient. And if it is positive trigonometric polynomial, then instead of focusing on coefficients, I can focus on finding out the matrix Q. What is the importance of this result? If there is an inequality on a trigonometric polynomial, which may be abstract or untractable, then I can translate that to a linear matrix inequality. How this LMI will be useful, we'll see this in the next slide very quickly. This is for a single dimensional trigonometric polynomial. If we are working in higher dimensions, which is our case, then just a notation that we have to keep in mind is we will be dealing with positive hyperoctane trigonometric polynomials that are used for multivariate or multidimensional cases. So the expressions, they become a little bit more complex when we go in the higher dimension. Okay, how do we use this property? So very first thing I had mentioned earlier that we'll look into the dual of that optimization problem. So here is the dual. Primal was minimized, dual is maximized. Primal had equality constraints, dual has inequality constraints. Let's look at the inequality constraint. It has that expression less than or equal to 1. You take the left-hand side on the right-hand side, you get 1 minus, and that expression is the dual of atomic norm. So 1 minus that dual of atomic norm greater than or equal to 0. If you expand it, it is a trigonometric polynomial greater than or equal to 0. In other words, we are dealing with a positive trigonometric polynomial. That inequality, I can write it in terms of linear matrix inequality using the this property that I had shown you earlier. And then I get this second equation. This second equation is the SDP, because if you have linear matrix inequality in constraints, you get an SDP. Now we have the SDP, even though it looks complex, but you can actually go to a computer, choose your favorite programming language, MATLAB, Python, C, and you can code this, and you can actually solve this problem. Once you solve this, you will get two polynomials as the output, one for radar, one for communications. The question is, okay, after solving all of this, now we have forgotten that our main goal was to estimate the parameters, the channel parameters. So how do I get those channel parameters? Here is how we get them. So if I have FR and FC, two polynomials. So before I show you in a plot how we get it, just for the sake of completeness, I want to show that performance guarantee, which tells us that. So it is encapsulated in terms of these proposition and theorem. I'll summarize what this means. You take these two polynomials, take their modulus, take their absolute value, plot it on the delay Doppler plane. And wherever that modulus achieves the value of unity, that is the location of the target or the channel parameter. You can compare this with what we call a CFAR detector in radar, where you have a post-process signal, you compare it with some threshold. If it is above that threshold, we call it target. If it is below that, noise or clutter. Here it is similar, except that the threshold is unity itself, that the value of this polynomial, or in terms of CFAR of the post-process signal, we want it to be unity within some numerical precision. So here's the result. We have these two polynomials, and we are searching for the peak in the delay Doppler plane, very similar to the CFAR, or if you combine CFAR with FFT in standard radar. So I take one of those regions, and then I zoom it up here. And in the inset plots, wherever it is unity, I put a plus sign on it. It turns out plus is right on top of the location of the true parameters. This is how we estimate the Doppler velocity and the delay, which translates to range. Once you have the channels, then it is no longer a blind deconvolution problem, it's a deconvolution problem. And then using methods such as least squares or some similar methods to solve linear system of equations, overdetermined linear system of equations, you can estimate the signals for radar and communications. In radar, we are not that much interested in the signal, but in communications, that was the unknown, right, to estimate the transmit message GP. There are many variations of this problem. You can have n-tuple blind deconvolution. If you have that, you will have those many linear matrix inequality as the number of emitters. When you add noise to the system, in that case, you have to add a penalty factor in your optimization. This could be further extended. Suppose the receiver is actually an antenna array. In that case, we have one more variable that we want to estimate, that is the direction of arrival. Then it becomes a three-dimensional problem. SDP usually takes a lot of time, so we have developed some algorithms to actually speed up this optimization problem. You can use spectrographs. We also have some recent work on using different types of interpolation function to actually make this faster. So all of those details you can find in the papers that I've listed here, but I'm not going to go into details of each one of these sub-problems. So this example demonstrates how very complex and deep signal processing theories, they come into play, even for a problem that appears rather simple, that is the spectral coexistence. We have not even looked into co-design yet. But there's a lot of scope for exploring signal processing research in this domain. That's what I wanted to show. Second example we look into is spectral co-design. Recall in spectral co-design, it's not just the receiver that we are working on, but also the transmitter. So here I've taken the example of automotive joint radar communications. We'll look into that bistatic example where we had a common transmitter, red car, common receiver, gray car. Usually in a vehicular scenario, it's the bistatic mode that people often look into, not just because it is more practical, but there's an inherent advantage to that. If both transmitter and receiver, they are on the same car, then the coverage of the radar is this red circle. The monostatic coverage is the circular coverage. But when it is bistatic, then you get range enhancement in one direction because the coverage of this bistatic system is an ellipse. So that is another reason that if you are analyzing ISAC in a vehicular scenario, you also get actually range enhancement if you do it in a bistatic mode. So the first question that we looked into this work, and this paper appeared in Transaction on Aerospace and Electronic Systems. It was a runner-up for the IEEE Barry Carlton Award last year. So here we started with investigating which waveform is more appropriate for automotive ISAC. Again, recall radar-centric versus communication-centric solutions. We can develop a new waveform altogether for this system, for this joint system. But then in automotive industry, they prefer to work with those waveforms for which they have chipsets. So with known waveforms. So we started with two known waveforms. One is radar-centric, that is phase-modulated continuous wave. And then second is OFDMA, which is more communication-centric. These are already in use by various automotive manufacturers. PMCW has this very nice property that it has its ambiguity function has this thumbtack shape. For people who may not be familiar with what ambiguity function is, you take a transmit waveform and then you correlate that waveform with its delayed and Doppler shifted replicas. The result is a main lobe and then some side lobes. Lower the side lobes, it's better because then you can distinguish two very closely spaced targets very well. So PMCW estimates range very well. It has a very good performance in range estimation. OFDMA has a very good performance in Doppler estimation if we use them standalone. But if we use them in a joint radar communications mode, that is, we take PMCW, embed communication symbols in that, then our first goal was to find out whether these properties they carry forward or not. So we derived their ambiguity functions. I'll spare the derivation, you can find it in our paper, but if we plot them, what do we notice? In the joint radar communications mode, both PMCW and OFDMA, they inherit the properties of their parent waveform. So even in JRC mode, PMCW has a very good range estimation performance. OFDMA has a very good Doppler estimation performance. With this knowledge, the next question is, how do we design the receive processing? So for receive processing, there are some commonalities between both PMCW and OFDMA if they act as a joint receiver. So I'll highlight some of the differences. Let's look into the PMCW first. I'll just summarize what is on this slide. So we are transmitting a common waveform, and then it interacts with these blue and yellow cards, and then at the receiver, the signal, if I simplify it, I get that four summation signal. What are the unknowns in this received signal that we want to estimate? Obviously, communication symbols, they are unknown. Range of the targets, Doppler velocity of the targets, and the angle of arrival of the targets. Now, it turns out angle of arrival in this case, you do simple Fourier beamforming, you can estimate the angle. Since it is PMCW, its performance in range estimation is still good. You apply a matched filter, you estimate your range. Then you are left with the Doppler velocity and communication symbols, which we cannot estimate very well in this system because in the residual signal, Doppler velocity is coupled with communication symbols. You cannot estimate them independent of each other. So this coupling, how to resolve this coupling? In our work, we suggested a form of multiplexing. Don't transmit joint radar communications for all the pulses in the PRI, in the pulse repetition interval. Some pulses you transmit radar-only pulse, that is without communication symbols, and the rest of the pulses you reserve for the joint radar communications transmission. If you do that, you can break this coupling because, as we show in our work, it gives you enough waveform identifiability at the receiver. So multiplexing can help with this. In OFDMA, again, if you do all the math and you look at that four summation signal, again, you have those four unknowns. Once again, angle of arrival can be estimated using simple beamforming here. OFDMA has a better performance in estimating Doppler. You apply a 50, you get Doppler. But it is the range here that gets coupled with communication symbols that we cannot estimate independently. Again, the solution is multiplexing, but now in the subcarrier domain, not in the time domain, in the frequency or subcarrier domain. So some subcarriers you reserve for radar-only transmission and the rest of the subcarriers for joint radar communications transmission. Then you can break this. If you look into the system design for this automotive ISAC system, the receiver is pretty much the same, except for which parameter is coupled. It's range for OFDMA and Doppler for PMCW. So you have a radar processor at the receiver, which will first estimate uncoupled parameters. And then the communication processor is trying to estimate the communication symbols from this jointly received signal. Obviously, because of contamination from Doppler, its estimation will not be perfect. Now it passes that information to radar, where radar removes the communication symbols. That removal may be perfect or imperfect if we don't apply any multiplexing. If you apply multiplexing, as I'll show in a moment, the communication symbol removal could be very close to perfect, but it cannot be removed completely. But if you don't do any multiplexing, then obviously this will be very contaminated signal. So after that removal, then the radar processor estimates the coupled parameter. The transmitter is obviously different for both of them because these are two different transmit signals. The only common part is the multiplexing, except that the domain in which we do multiplexing is different. For PMCW, it's in time domain, some pulses for radar-only transmission, some for joint radar comms. In OFDMA, it's in the subcarrier domain. To show you the effect of this multiplexing, here is an example, which so for OFDMA JRC, I'm plotting the error in the estimation of range because range was the coupled parameter there. For PMCW, the coupled parameter was Doppler, so I'm plotting the error in Doppler. Let's focus on figure B. So the red curve is the, so this plot is the estimation error versus SNR. Red curve is the case when the communication symbol removal is perfect in radar processor. So that's a theoretical performance. That's the theoretical curve. Now, if we don't do any multiplexing and we try to estimate this coupled parameter range, then that curve is the blue curve. As you can see, when the SNR is high, the blue curve approaches the red curve. But these are low SNR systems. Radar definitely is a low SNR system. So at low SNR, then that blue curve departs from this red curve a lot. How can we narrow that gap? You do multiplexing. So that is the gray curve, where half of the pulses are for, or subcarriers are for radar-only transmission, and half of them are this joint radar comms. If you do that, then it helps in narrowing that gap, especially at low SNR. So this shows that multiplexing is not only essential, it's also actually practical in these kind of systems. So this is an example of co-design and where it highlights the importance of choosing the right waveform, but just choosing the waveform is not sufficient. At the receiver, usually you need some way to separate the radar component from the communications component. So now this is the time when I press the panic button, but in my case, it is just going to that last example. So this is a very good point to go to that last example, which is very interesting, that is the opportunistic ISAC. So we looked into spectral coexistence, very theoretical example. We looked into spectral co-design, mix of theory and practice. Now let's look into a very practical example. Here it is related to weather sensing, which a lot of speakers have talked about today. This is opportunistic ISAC. So remember, opportunistic ISAC is you already have infrastructure for one of the functionalities. Now here, the infrastructure is for communications, and we would like to use it for radar. Here's the problem that we looked into. So usually weather sensing is done using a weather radar. For example, there are about 140 S-band weather radars operated by National Weather Service in the contiguous United States. These are very big, expensive systems. In Europe and Canada, they are C-band. Even though theoretically they cover the entire country, practically there are gaps because their range is 250 kilometers, but then after 80 kilometers, the lowest elevation beam is already touching the cloud tops, while most of the interesting activity, rain or precipitation is happening in lower troposphere. So in practice, we have gaps, even using weather radars. Then there are a lot of parts in developing economies in the world where we do not have any weather radars because these are expensive systems. So globally, obviously, there is a lot of gap, theoretical as well. How can we address it? So we worked with this one European wireless service provider whose name I'm not supposed to reveal, but I can talk about the research. They operate these communication satellites. Now, the communication satellite signal comes from the satellite, goes through the atmosphere, and then is received by the ground terminals. So they said that we can provide you how much power is received at the ground terminals. And as the signal propagates from space to ground, it loses its strength when it interacts with the rain medium, or it suffers attenuation, in other words. So if we know the amount of attenuation, that should be proportional to the amount of rain. Can you use that information to estimate the rainfall rate? That was the problem. Now, this is very attractive because compared to just few weather radars on ground, we have 300,000 such terminals in Europe and about 2 million worldwide. And this data about how much power is received versus the power transmitted, and the difference tells us the attenuation. That data is available with central servers of various companies. So that was the challenge. Can you use this attenuation data to estimate the rainfall rate? Now, normally, now these satellite links, they are in millimeter wave, actually KU band and a little bit between KU and KA, I would say. So we call 30 to 300 gigahertz as millimeter wave. So in millimeter wave, we have a linear relationship between rainfall rate and specific attenuation. Specific attenuation is the first derivative of attenuation with respect to range. That is AH. But this linear relationship gets perturbed more often than not. If there's wind shear, if the storms are convective storms, and so on. So it doesn't remain like we cannot use that simple linear relationship to estimate rainfall rate. It will be highly inaccurate. Weather radars get a lot of other information to very accurately estimate rainfall rate. They get Doppler velocity. If it is a polarimetric weather radar, then they get differential reflectivity, a lot of other polarimetric variables, and can give very accurate rainfall rate. Here, all we have is the power received versus power transmitted. That is only the attenuation. So how can we use this to estimate rainfall much better? Now, it's an information deficient scenario. Now, someone was saying everyone is interested in AI these days. So in all the presentations these days, there comes a point where you encounter deep learning. In my presentation, this is that point. Because it is information deficient scenario, we turn to deep learning networks. So what we are going to do, we'll train a deep learning network with the nearest weather radar on ground. And then in the prediction stage, we'll feed the communication satellite attenuation data and see what it gives us. So we did this very first experiment in Southwest Germany. So this is the region, the box that you see, about like 30 terminals there. And then we train them with this network, LSTM network, with the nearest German Weather Service or DWD radar data. Here is the result for just one terminal. The bottom plot is the instantaneous rain rate. So blue is the DWD radar. And then the satellite link after this trained neural network is in red. You see it very closely follows DWD data. This is not the data that meteorologists use. They use accumulations, that is the cumulative rain rate, that is plotted in the top plot, where as time elapses, we see that the gap between satellite link and radar, it grows. Our goal is to actually narrow this gap as much as possible. How do we do that? Before I come to that, let's see what if we do this training for all the terminals in that region, and then we can generate a rainfall map, how that rainfall map looks like. So this is for one of the events that occurred in 2018, May 2018. So on the right side is what the DWD radar is seeing, a storm moving towards the northeast. And our satellite link neural network trained version is shown on the left side. Clearly, they don't match. Radar is always going to be accurate, but all we see is this blob following the direction, maybe the relative strengths, but they don't match at all. So we want to improve this. Now, how can we improve this? So people who work with neural networks and deep learning networks would know, if you have a lot more data, you can actually make this more accurate. So far, we dealt with only 30 terminals in Southwest Germany. Then we got access to data from France, where we had access to about 12,000 terminals, data from 12,000 terminals. So, and we also changed our neural network from LSTM after a lot of this hyperparameter tuning to CNN, but some different versions of CNN. You can find details in our paper. Here is what the results look like. So the top panel that you see on the right side is the satellite link. Left side is the Meteo France accumulation data. They match very well. Then the lower two panels is every 3 hours comparison of radar versus this CNN trained satellite link data. And again, even every 3 hours, we see that it is much closer to radar. The next is this video, where on the right side, again, the satellite link, every black dot is the location of that communication satellite terminal. And I'm comparing this with the Meteo France data, very similar intensities. Circulation is also covered very well by the satellite link. And even if some of you can see some black dots, they sometimes vanish because of the outage in the terminal. even in that case, because it's a combined operation of so many terminals, we are able to estimate rainfall even in those locations where there was outage in those communication satellite terminal. So this is a very good example of a very practical example of ISAC, where we have existing communications infrastructure. We take help of the nearest weather radar to train the network, and then use in the prediction stage data from communication satellite, and then use the final product to complement the observations of that same radar. So we have done this for a few other countries. So Germany, as I mentioned, we have done this. Currently, we are doing this for Brazil. We are trying to do this for Switzerland. It's a more challenging case because of mountainous terrain there. But then this is very useful for the developing economies of the world, where there may not be any weather radar available, but you can use these trained networks and use the data from the communication satellite terminals in those cases. All right, so this brings us to the end of this presentation. So I covered these three major paradigms in ISAC, but obviously there is a lot more work going on in this area. There are many different types of ISAC architectures. So like I said, in this distinguished lecture series, sometimes I cover just one of them in more detail. For example, distributed full duplex. If there are multiple radars, multiple communication terminals, then how to do ISAC using intelligent surfaces. Also using OFDM or 5G waveforms to measure the heart rate or perspiration rate of drivers and other passengers, which I had alluded to in the very beginning of this presentation. So that is ISAC-based VSM. A few more architectures here, like drone-based ISAC. We have done work on that too. I want to emphasize one aspect here, that when we open spectrum for both radar and communications to share, then the privacy of communication users and the security of military radar systems could be compromised. So there is also recent work on secure and privacy preserving ISAC, and we have also done some work on that topic. All right, so at the end of every YouTube video, you have like, share, subscribe. Now, this is not the YouTube video, but if you're interested in my work and my research, please feel free to connect with me or follow me on LinkedIn at this handle. And we have done quite a few books on this topic. So very first one was published last year by Wiley IEEE Press. There are a lot of chapters. I didn't cover a lot of other information like information theoretic scenarios. You can find all that information there. You might have guessed I have interest in weather radars. Indeed, we published a 3-volume compendium on advances in weather radar last year with IET Press. So there's a lot more information there. And with this, I would like to thank you for listening and for inviting me to this talk. And I'm happy to take any questions you guys might have. Thank you.